Hello, good evening, and good morning again. This is your host, Mike Espina. Welcome to Math Agility Live. This is our new platform where students can send in their math homework problems to our social media channels. And we will answer them via Facebook Live every Tuesday and Thursday. That's from 6 p.m. to 8 p.m. PST, Wednesday and Friday, 9 a.m. to 11 a.m. Manila time. So tonight we will have a special guest. We will be tackling differential equations, and we will give you some tips and techniques on how to solve this kind of equations. And also, we will solve some word problems regarding differential equations in second order and also in first order linear differential equations. So, our guest for tonight, of course, you already have known him. I guested him last time here. He's a graduate of BS Civil Engineering at St. Louis College in La Union. He's also a national quizzer for math and engineering, and he is a certified Vedic math teacher. Please, a warm welcome to Daniel James Molina. Daniel, can you please say hi to our
Good
viewers?
morning, everyone. Hello to the Math Agility followers and viewers.
Okay, thank you. So before we start, let me just share my screen to you. Or Daniel, do you want to share your screen so you can solve right away the equations?
It's fine, sir.
Okay.
Okay, sir. I'll just share my screen. All right. So it's a blank page, sir. Can you see my screen?
Yeah.
Is it
Good.
clear?
Mm-hmm.
Okay. So I'll start right away, sir.
Sure. Yes.
Okay. Okay. So our first problem for today is this differential equation. So we have x, the x minus y squared dy is equal to 0. Okay. So noticing from our problem, this is already a variable separable differential equation. Okay. So a variable separable differential equation can be rewritten in the form of, we have here a function m in x and y. So m dx plus n, oh, sorry, it should be m only. M dx plus n dy is equal to 0, where m here is a function of x and n is a function of y only. Okay, so if you can write the problem, the equation into this form, then it is considered as a variable separable differential equation. So this is actually one of the easiest equations, types of differential equations to solve. Okay, so once you have separated the two variables, that is by pairing the variables into its differential, which is already done in this problem. As you can see, we have x paired with dx and negative y squared paired with dy. So it's already separate. The variables are already separated. So to solve for this equation, if I'll just write it here. We have x dx minus y squared dy is equal to 0. So to solve for this equation, we just have to integrate um, the two sides of the equation. So we have to integrate the first term here, and then minus we have integral of this one, and then the integral of the right hand side. Okay, so the integral of the first term, we have 1/2 x squared, that is from power rule. Okay, we'll just disregard the arbitrary constant first. Okay, so integrating the second term, we have 1/3 y cubed. And then the arbitrary constant will be found at the right hand side. So actually the integral of 0 is a constant. Okay, so we'll just have to write it as C, okay, as the arbitrary constant. Okay, so to simplify further, we'll just eliminate the denominators, okay, eliminating the denominators by multiplying the least common denominator, that is actually 6, okay. So multiplying by the whole equation by 6, we have 3x squared and then minus 2y cubed is equal to, this is actually 6 times c, right? But 6 times c, or 6 times an arbitrary constant, is also a constant. So we'll just write it as c. And that is actually our final answer. Okay, that is already our general solution. Okay, this is called the general solution. Since we don't have any initial conditions, so this is our final answer. So that's for the first problem. Okay. So let's have another problem for variable separable variable separable differential equations. Okay. So the second problem here is actually dy, that is equal to 2 times t times the quantity y squared plus 9 dt. Okay, so we can, as you can see here, we have y squared plus 9. This, the whole term y squared plus 9 is paired with dt, which cannot be done, which cannot be solved right away. So what we can do here is by and then relocating it to dy. So we pair it with dy by simply dividing the two sides of the equation by y squared is 9. Okay. So by dividing it, we have, as you can notice here that the term y squared plus 9 is cancelled. So the differential equation will be dy all over y squared plus 9. And that is equal to 2t dt. Okay, so we already have separated the variables. So we actually don't need to rewrite that one in this form, the original form a while ago. As long as, okay, as long as we can separate the two variables. Okay, so to solve for our differential equation, we just have to integrate the two sides. Okay, so integrating the left hand, this is actually, I'll just write it here. So the left hand side will actually be 1/3 the inverse tangent of y over 3. Okay, and then the right hand side, using the power rule, that is t squared. And then, of course, we must not forget our arbitrary constant. Okay, and then by using algebra, by solving for y, we have y that is equal to 3 tangent of the quantity 3t squared plus c. Okay, so that is from algebra solving for y. And that is our general solution. As long as you can solve for the expression for y, okay, once you can solve for y, you can do that as long as our solution is simple, as you can see, okay? But once the value for y, the expression for y is not solvable, then you can rewrite the general solution as is, okay? So that is our answer for the second problem.
Okay, thanks, DJ. Okay, let me share my screen to you. So right now we're gonna solve a word problem from differential equation. So can you see my virtual board? Can you see my screen?
Yes, sir.
Okay. All right, so let's first read the problem. Five mice in a stable population of a 500 are intentionally infected with a contagious disease to test a theory of epidemic spread that postulates the rate of change in the infected population is proportional to the product of the number of mice who have the disease with the number that are disease free. Assuming the theory is correct, how long it will take to have the population to contract the disease. So the first thing we need to do is let's define the variable. So if nt is the number of mice with disease at any time t, and then we have an initial condition of n at time 0, we already have 5 mice uh, who got infected with the disease, and then so we can compute the number of uh, disease-free mice. So mice who are disease-free at any time t. Time t. Okay, so based on the problem, we can see that it's a proportionality equation that we can create here. Hold on. So let's read that part. It says in the second portion that's the theory of epidemic spread that postulates the rate of change in the infected population is proportional. So we will use the variable k actually in our equation. So if we define dn over dt equals k, so that's our constant of proportionality, and then n times 500 minus n, because it says the product of um, disease-free mice and the number of mice with disease, right? So n times 500 minus n. So let's try to, this is separable. So this is what DJ showed to you how to solve this kind of equation. So dn, let's put n over 500 minus n equals um, kt, and then let's move kt to the left hand side of the equation. So dn n oops quantity 500 minus n minus kt equals 0. Okay, so uh, we can see that we can use partial fraction decomposition for this part of the equation, which is 1 over n 500 minus n. So let me write it here. Use partial fraction decomposition. So let's equate it to a over n plus b over n 500 minus n. Okay, so let's multiply the whole equation, left and right of the equation, by n times 500 minus n. So definitely this would be equal to 1. A will multiply to 500 minus n, and then b will be multiplied to n. So let's distribute a. This is still equal to 1, so 500a minus na plus or nb, and then let's combine all the constants and the variable n. So of course this is still 500a, and then if we collect the n from this last two part of the equation, so this would be, let's say, plus n, so negative a plus b. So let's use comparing the coefficient from the left side of the equation. Of, hold on. Can you see this? So let me just scroll it up. So let's compare all the coefficient from the left-hand side and the right-hand side. So we can see that 500A would be equal to 1, which is the constant. So we can solve for the value of A. So A would be equal to 1 over 500. And then since there's no n, the value of n on the left-hand side of the equation, negative A plus B would be equal to 0, right? So we can say B is equal to A. And since we know A here, we can say B is also equal to 1 over 500. So let's go back to our partial decomposition. So here, so we know that both of them have a constant of 1 over 500, right? So let's let me write it here. 1, oops, sorry. So 1 over n 500 minus n is equal to 1 over 500 over n plus 1 over 500 again over 500 minus n. Okay? So now let's try to factor out 1 over 500. So from the equation, from the differential equation, so earlier, so let me show you again. This is our equation, right? So let's say this is equation 1. Okay. So since we decompose the dn over n over 500, so this would be 1 over 500, 1 over n plus 1 over 500 minus n dn minus k dt equals 0. So we can integrate now. So integrating the equation. So let's say 1 over 500 integral of 1 over n plus 1 over 500 minus n, of course, dn minus integral of k dt equals 0. Okay, so this would mean 1 over 5, oops, 1 over 500 ln of capital N, so minus ln of 500 minus n. Okay, so later on you will distribute 1 over 500 to both the quantities here. So this would now minus 80, of course. And this would, let's equate it to an arbitrary constant c. So let's take out 500 from the logarithmic part. So of course, this two variable here with, let's move it on the left, on the right hand side. So kt would become positive, so plus c. And then the 500 here, so this would be 500. So what's left here would be the logarithmic part, ln of n minus ln of 500 minus capital N. And we can combine this further. So ln of quantity n over 500 minus n. So our goal is to compress all the logarithmic parts. So when we take the exponentation, when we take e of both sides, so let's do it. So let's raise both sides to e. So we have n over 500 minus n would be equal to e 500 KT plus C, right? Okay, we can still distribute this exponent. So let's do that. So 500 minus n e to the 500 kt e 500 c. So let's call e to the 500 c as c sub 1. Okay, so let's say c sub 1 is equal to e equals to 500 c. Okay, so our equation now would become n over 500 minus n c sub 1 e 500 kt, right? Okay, so we have an initial condition given. So at t0, it says our n is 5. So the mice who got infected by the disease is 5. So let's substitute this in equation 2. So this is our equation 2. And substitute. Okay, so at t0, so this would be n 500 minus n, and then c sub 1 e 500k 0. Okay, so n is 5, sorry. So let's put 5 here and 5. Oops. So this is 5 over 495 equals c sub 1. So effectively, the exponential part would be 1. So c sub 1 is equal to 500, 5 over 495, or if we simplify it, it would be 1 over 99. So hence we have, so our equation would now be in this form, since we already solved the arbitrary constant c here. So 1 over 99 e to the 500 kt. So there is a question there, if the population that will be infected becomes uh, half of the population becomes infected. So total population given is 500, right? So half of this is 250. So the number of n, or the number of mice that got infected, would be 250. So, and we need to solve for t. It asks you to solve for t. So this is the second problem. So again, from our equation, so let's try to substitute 250, 500 minus 250, 1 over 99 e to the 500 k t. So this would be 1, right? Because the denominator would become 250 as well. So this is 1. And then let's cross multiply 99. So whatever on the right hand side will be the exponential form, 5kt. So let's take away the exponential by taking ln of both sides. So ln of 99 is equal to 500 kt. Okay, therefore t is equal to ln of 99 over 500k unit of time. So this would be the answer for when it reached 250 for all the mice that will be infected by the virus or by the disease. Okay, let's go back to DJ to do again solving two equations, two differential equations.
Okay, so let's continue. Let's continue our discussion. Let's have this problem. We have here y prime that is equal to x squared plus y squared So we can rewrite it as that is equal to on your we can prove that this equation is not variable separable. Okay, so since it's not variable separable, so we can use other methods. Okay, uh, wait a second. So by using other methods, we have to try first. We have to try first this method. Actually, we have to try verifying if this differential equation is a first is homogeneous differential equation. Actually, we also have other forms, other types of differential equation which are exact, not exact, and the like linear ordinary differential equation, Bernoulli, and so on and so forth. But we can actually use here the homogeneous. How? We can prove that by using this substitution. So we have y that is equal to kx. Or actually, we can also use k is equal to, x is equal to ky. But for this problem, we'll try y is equal to kx, where k here is also a function. Not by having this substitution, we can try to differentiate both sides. We have to differentiate, and then we'll use implicit differentiation. So for the left hand side, we have dy over dx. Okay, and then on the right hand side, we'll use the product rule. So differentiating it with respect to x, we have k times the differential of x, that is 1, and then plus we have x times the derivative of k, we have dk over dx. Okay, so using these two substitutions, we have our equation here as, we can write it as, we have the left hand side k plus x dk over dx, and that is equal to x squared plus y squared, but y is equal to kx, so we have k squared or x squared. That is also, we have the denominator x times kx, or that is actually kx squared. Okay, so simplifying our right hand side, we have here 1 plus k squared over k. So we can transpose. So we have 1 plus k squared over k minus k, or k minus k. But if we will try to simplify this, we're using our algebra, this is actually 1 over k. So we will write the equation x dk over dx, that is equal to 1 over x. And you can notice here that we changed some of our variables. So from y and x on the original equation, we transformed it into uh, a differential equation in terms of k and x. But as this from equation, we can rewrite further. Let's say equation. We have tk that is x. Here we can conclude that this is a variable differential equation. So our here from a complicated, we transform it variable separable equation, integrate this. So the integral of the left is 1/2 k squared. That is equal to the integral
Okay. Um, I think DJ was disconnected from the Zoom link. Okay, let me just share again my screen. I will wait for him to come back. Okay, there's a question in our Facebook page about it should be DT. Yes, sorry about that. So this part here should be DT. So I forgot to put D. So DT, and of course on this part it should be DT as well. Right. Thank you for correcting me. And DJ is already here. So I'll give him again the floor to to show his solution. DJ, you can continue your solution if you can share your screen, please. Okay, he's connecting now. Okay, you can continue, DJ.
okay. Okay. Sorry. Sorry, sir. Alright. So continuing our discussion, okay, our solution. So we end up I disconnected on this part. So I have already integrated the left hand side and the right hand side, which is equal to 1/2 k squared. That is equal to the natural log of the absolute value of x. And then, of course, our arbitrary constant plus c. Okay, so we can rewrite our equation by multiplying 2 to just to eliminate the denominator. Okay, so we have k squared that is equal to 2 the natural log of absolute value of x plus 2c, or that is of course an arbitrary constant c. Okay, but we have a while ago our substitution y is equal to kx. Okay, since our original differential equation is in terms of x and y, so we also have to express our final answer in terms of x and y. So solving here for k, we have y over x. Okay, so substituting it to our equation, we have y squared all over x squared. That is equal to 2 natural log of x plus c. And then solving for y squared, we have the equation or the expression x squared times the quantity 2 natural log of x plus c. Okay, so we need not to solve for y by taking the square root. We'll just have to express our final answer or our general solution as this one. So this is the answer to our differential equation. Okay, so let's proceed to the next problem. Okay, so the next problem, we have the equation x squared plus 1 dx plus 1 over y dy that is equal to 0. But we have here already an initial condition, that is y of -1 must be equal to 1. Here we have, I'll just explain this one, this initial condition. It only means that when the value of x is -1, the value of y is equal to 1. All right. So to use these two initial conditions, we'll solve our differential equation first. So we can notice from our differential equation that the variables are already separated. So it's a variable separable differential equation. So we integrate both sides of the equation. Okay, so the three terms here. The first integral by power rule, it will be 1/3 x cubed plus x. And then our second integral will be the natural log of y. And of course, the right hand side is our arbitrary constant c. Okay, so actually, this is our general solution. But since we have an initial condition, then we must have to substitute our initial condition to our general solution, so that it will yield to a particular solution. Okay, so by substituting the values of x and y into our equation, we have 1/3 times -1 cubed plus -1. Those are the values of x. And then plus the natural logarithm of y. Actually, the value of y is 1. So that is equal to c. And from there, we can solve for the value of c that is equal to -4/3. Okay. So let's substitute the value for the constant into our general solution. We have 1/3 times x cubed plus x plus the natural logarithm of the absolute value of y, that is equal to -4/3. And then let's eliminate the denominators by multiplying 3. So we have here x cubed plus 3x plus 3 natural logarithm of the absolute value of y. And then we transpose -4 on the right side. We'll transpose it to the left side so that we have +4 on the left side, that is equal to 0. And actually, we can have this as our final answer already. But if you want to solve for y, then we can transpose the three terms here, okay, x cubed, 3x, and 4 to the right hand side. We have 3 natural log of the absolute value of y, that is equal to -x cubed minus 3x minus 4. So we have to divide it by 3. So natural log of y, that is equal to -1/3 times the quantity x cubed plus 3x plus 4. And then let's raise these two uh, expressions into the base e, by the base e. So we have the absolute value of y equal to e raised to this complicated expression here. But we can rewrite this one, okay, in terms of this notation. Exp for exponential. Okay, I'll just rewrite it properly. Exp of the function or of the expression -1/3 x cubed plus 3x plus 4. So we can have this answer, but we can also have this one. Both are actually correct. So, okay, so those are our solutions. Um, Back to you, sir.
Okay, thank you, DJ. If you have any questions or comments, please write it down at our comment section or on our Facebook and our Twitter and Instagram account. So let me share again my screen. So this is the word problem. A tank initially holds 100 gallon of a brine solution containing 1 pound of salt. At t equals 0, another brine solution containing 1 pound of salt per gallon is poured into the tank at the rate of 3 gallons per minute, while the well-steered mixture leaves the tank at the same rate. So we have two questions here. Find first, A, the amount of salt in the tank at any time t, and then B, the time at which the mixture in the tank contains 2 pounds of salt. So this is called a dilution problem, and this is still a linear uh, first order linear differential equation. So let's try to draw the situation mentioned in the problem. So we have initial volume of 100 gallon of brine, and then it contains 1 pound of salt initially, and then it's adding another brine solution at T0. The brine is 1 pound of gallon, 1 pound of salt per gallon, and then the rate that it adds this brine solution to the container is at 3 gallons per minute. Okay, so for a dilution problem, um, we have set up an equation in the form of dq over dt plus f over v sub o plus e minus f times t, and then times q equals be. So what are these variables here? So q is actually the amount of salt in pounds at any time t. And then BE is the rate of pounds per minute of salt uh, entering the tank or entering the container. And then VO is our initial volume. ET is volume of brine added. ET. E times T is the volume of brine added. And then EF is the volume of brine removed. Added and then removed. And then A is the volume of salt. A, volume of salt. Okay, that's it. So let's have listed what is given in the problem. So given case, we have the 100 pound, uh, not pound but gallon, I think. Yeah, gallon is volume, 100 gallon of brine solution, and then we have A initially of 1 pound of salt, and then B is also 1 pound of salt per gallon, and then our E and F, E is equal to F is equal to 3. So let's set up the equation and substitute the given values. So dq over dt plus 3, oops, let me write it clearly. So 3 over 100 plus 3 minus 3 times t, and then the q equals to 3 times 1. So of course this would be 0. So let's simplify this. So dq over dt plus 3 over 100 q equals 3, right? So let's move the variable q to the right hand side of the equation. So we will have dq on the left. So negative 3 over 100 times q plus 3. Okay, let's factor out 3. So 3, negative 3. So q over 100 minus 1. And then what can we do here? Let's divide this both sides by, oops, q over 100 minus 1, both sides by q over 100 minus 1. So this cancels out. We have dq dt all over q over 100 minus 1. And this is equal to negative 3. Okay. And then the next uh, step is to integrate. So let's integrate this. So integrating. So integral of dq over q. Dq over dt. Dq over dt all over q over 100 minus 1 dt up. I forgot to put dt here. Sorry. And then negative 3 dt. Okay. And then let's get the common denominator, 100 to the quantity below. So dq over dt all over q minus 100 all over 100 dt. So this would still be negative 3 dt. And then let's do a little bit of substitution. So let u is equal to qt minus 100, or just q is okay. So du would be dq. If this is respect to t, okay, let's put it so this be clear. dq d minus over dt, right? So let's try to substitute that in our integral. So let's take out the 100. So that's 1 over 100. And this will be du over u is equal to negative 3 dt. So this means this is 1 over 100 ln of u and negative 3t. So, and let's put back what the ever the variable of u is. So 100 ln of q minus 100, right? Q of t minus 100. So next step, let's put 100 up. Of course, we have the C1 here, sorry. Plus C1 plus C1. So let's put 100 to the right hand side. So when we raise the natural log to e, it will be easier for us to take out or extract whatever's inside this parenthesis here. So ln q of t minus 100. So times 100 negative 3t plus c sub 1. Okay. So let's raise this both side of the equation by the exponent e. So this becomes q of t minus 100 e to the negative 300t and e 100 c sub 1. Okay. So let's call c sub 1 or let's say c sub 2 equal to e 100 c sub 1. Okay, let's rearrange. Q of t minus 100 equals, so C sub 2 E negative 300t. And then let's transpose 100 to the right-hand side of the equation. So Q of t would be C sub 2 E to the negative 300t plus 100. Okay, so since we have a initial condition that at t equals 0, we have Q initial weight of the salt is 1 pound, right? Yes. So 1 pound. So that's A equals 1. Q is equals to 1. So at Q equals 0, C sub 2 is E to the negative 300 times 0 plus 100 is equal to 1. So let's solve for C2. So C2, so this would effectively be equal to 1 equals to 1 minus 100. So C2 is equal to negative 99. So let's write this arbitrary constant that we solved to the equation, to our solution. So Qt is equal to negative 99 e to the negative, hold on, why did I get 1 over 100 here? Okay, it should be 100, sorry. So this should be 100 instead of 1 over 100. 100, 100. So in effect, this would be um, negative 300 over 100. So this is negative 3 over 100 and C sub 1 over 100. Okay, so C sub 2 is equal to C sub 1 over 100. So C sub 2 is e to the negative 3 over 100 again. 3 over 100t. So this is 3 over 100t again. So we have, okay, same thing. It's 99, but instead of e should be raised to negative 3t over 100 plus 100 here. Okay, 100. Okay, so this is our solution. And for letter B, the question is what time will it reach Q is equal to 2 pounds? So for letter B, what time will it reach when Q is equal to 2? Right, so let's solve it. So substitute in our solution. So 2, oops, 2 is equal to negative 99 e to the negative 3t over 100 plus 100. Okay, so let's move transpose 99 here, 3t over 100, and then 100 minus 2. So this would become 98 over 99 e to the negative 3t over 100. So let's take ln of both sides, the natural logarithm of both sides. So this would equate to negative 3t over 100 ln of 98 over 99. Oops. So t would be equal to 100 over 3 and then the negative ln of 98 over 99. So when you take or calculate this in your calculator, this would be equal to 0.338 minutes. All right. So if you have any question, please write down at the comment section below of our Facebook page, Twitter account, and Instagram account. Okay, so let's go back to DJ again to solve other differential equations.
Okay, so let's continue solving some differential equations. Okay, let's have this problem. We have here one y prime that is equal to 2 plus ye raised to xy all over 2y minus xe raised to xy. Okay, so again, let's rewrite y prime into dy over dx. Okay, equals 2 plus ye raised to xy all over 2y minus xe raised to xy. Okay, so notice on the problem that this differential equation is not variable separable. Of course, we have the exponent of that is xy. We cannot simply separate the two variables there. Okay, and then it's not also homogeneous. Okay, if we try to have y equals kx or x is equal to ky here, we cannot eliminate one of the variables. Okay, so what we can do here is let's try to rewrite it in terms of this form. Okay, we have here m dx plus n dy, and then we'll try to work from there. Okay, so m and n here and n here uh is already in terms of x and y. Okay, these are expressions in x and y. Unlike the variable separable a while ago, m is in terms of x and n is in terms of y. So this time it's not. It's both m and n are in terms of x and y. So by writing the equation and then let's simply using algebra here, we have 2 plus ye raised to xy dx plus xe raised to xy minus 2y dy is equal to 0. So from our equation, we have m that is equal to 2 plus ye raised to xy, and then we have n that is equal to xe raised to xy minus 2y. Okay, so if we cannot solve the equation by separation of variables or by the homogeneous DE substitution, then what we can try is to see or is to solve the condition wherein the given differential equation is exact or not. Okay, how will we be able to solve to show that the differential equation is exact? Then we'll try to take the partial derivative. Okay, so for m, since it is paired with x with dx, then let's take the partial derivative of m with respect to the other variable. It's y. Okay, that's the variable y. So that is equal to, of course, 2 here will be 0. And then for the first term, the second term, since it will be differentiated with respect to y, then we will have to use the product rule. Okay, so y e raised to xy, partial derivative with respect to y, will be e raised to xy plus xy e raised to xy. Okay, so by taking the partial derivative here, we must consider x as a constant. Okay, similarly for n, we take its partial derivative but this time it will be with respect to x. Since it is paired with dy, so we'll take its partial derivative with respect to x. The partial derivative will be e raised to xy plus x e raised to xy. So actually, the first term by using a product rule, it will be the partial derivative. Okay. Oops, I forgot to write xy here. Okay, xy e raised to xy, and then of course negative 2y will be a constant since we are taking its partial derivative with respect to x. Okay, so the derivative of a constant is 0. So note this that the two partial derivatives are equal. Then once that the partial derivatives are equal, then the differential equation is exact. So to solve for exact linear differential equations, once it's proven, then we'll just have to actually different integrate. Okay, integrate. Let's try to integrate the first term. So that's 2 plus y e raised to xy dx. Let us integrate this one. So since we have here dx, so we will integrate with respect to x. So y will be a constant, right? So integrating with respect to x, we have 2x, okay? And then for the second term it will be e raised to xy. Okay, you can use substitution or by correction factor since y is a constant here. Okay, and then for the second term, we have here a small twist. Okay, let's first rewrite the second term. Okay, x e raised to xy minus 2y dy. So before we evaluate the integral, okay, we will disregard the terms with x. Why will we disregard the terms with x? Because we have already integrated with respect to x. Okay, so we disregard x here. It's actually like a cheat code. Okay, all right. It's almost illegal, but it works. Okay, so we end up integrating negative 2y dy. So that is equal to negative y squared. Okay? So for our general solution, what we will do here is to simply add the two results. This one and this one. We'll add. So that is 2x plus e raised to xy minus y squared. Okay, adding the two expressions. And these two will be equal to 0. 0. So this will be our general solution. Okay, so that's for exact differential equations. Let's proceed to the next problem. Okay, another we have actually another exact differential equation. Okay, so we have x dot, or that is actually the first derivative of x. We have sorry, that is equal to the quantity 2x squared x minus t all over. We have 4x cubed minus 6x squared t plus 2x t squared, and we have an initial condition that is x of 2 is equal to 3. So again, our initial condition here, we have at t is equal to 2, we have a value of x that is equal to 3. So this x dot with that at the top is actually the first derivative of x with respect to the independent variable, which is t. Okay, so we write this one, 2x squared, x minus t. Okay, that's all over 4x cubed minus 6x squared t plus 2x t squared. Okay, so again, you can verify on your own that the differential equation is not variable separable. At the same time, since okay, since the degree is 3, okay, so the degree of our numerator is 3, and of course the degree of the denominator is also 3. So we can actually use homogeneous differential equation, the method for homogeneous differential. But for easier, for more convenient solving, okay, we'll have to try to prove that this is also an exact differential equation. Okay, so writing our equation, we have 4x cubed minus 6x squared t plus 2x t squared dx plus 2x squared t minus 2x cubed dt, that is equal to 0. Okay, so from our discussion a while ago, we have here m, okay, that is equal to 4x cubed minus 6x squared t plus 2x t squared. And then we have n, that is equal to 2x squared t minus 2x cubed. Okay. You may be wondering why didn't I cancel some of the common terms? We'll look in a bit. Okay. So let's try to take its partial derivatives. Okay. So partial derivative of m, since m is paired with x, so we'll take its partial derivative with respect to t. Partial derivative of m with respect to t, that is actually negative what? Negative 6x squared plus 4x t. Okay? And then for the partial derivative of n with respect to x, okay, it will be 4xt minus 6x squared. So as you can see, it the two partial derivatives are equal. So our differential equation is exact. Okay? So let's integrate the two terms. Let's try not to have the twist a while ago. Okay? Let's try to integrate the first term. 4x cubed minus 6x squared t plus 2x t squared with respect to x. So from here, from this integral, the variable t will be considered as a constant. Okay, so the integral of the whole expression is actually x to the fourth minus 2x cubed t plus x squared t squared. So all of those are by power rule. Okay, let's integrate the second term without disregarding anything. Okay, so let's copy the whole expression. 2x squared t minus 2x cubed dt. So here we will integrate with respect to t. So x here will be considered constant. So integrating, we have x squared t squared minus 2x cubed t. Okay, so from these two results, we can see that we have common terms. Okay, x squared t squared and negative 2x cubed t. Since these are the common terms, then we'll just have to copy the common terms. We did not to add. Okay, we'll just copy the common terms. So we have x to the fourth and then minus 2x cubed t. It's just like getting the union of two sets. Okay, will overlap common elements, something like that. Okay, so we have x to the fourth minus 2x cubed t plus x squared t squared. Now we'll equate that to the arbitrary constant c. So as you can see in our general solution, we don't have any denominators. That is actually The reason why I did not cancel any common factors, we have a common factor of 2 here, right? Oops. We have a common factor of 2 in our original differential equation. We have a common factor 2. If we will divide the whole equation by 2, then we will arrive at a general solution with fractions. Okay, but you'll just have to multiply it again by 2 to eliminate the denominators. Okay, and then you can also cancel the common terms which are variables x and t. We have common terms there. Okay, the given equation, the common term, the greatest common factor here is actually 2x. Okay, so you can also cancel 2x there, but I think it will end up a with an inexact, not exact differential equation. So you will end up multiplying it again by x, then proving that it's an exact differential equation. Okay, so this is our general solution, and I'll just write the initial condition. Here we have x of 2 is equal to 3. So we'll substitute t that is equal to 2 and x that is equal to 3 so that we can solve for the arbitrary constant. Okay, so we have 3 raised to 4 minus 2 times 3 cubed times 2. Okay, plus x squared, we have 3 squared, and then t squared, we have 2 squared. That is equal to c. So solving for the arbitrary constant c, we have the value 9. So therefore, substituting it to our general solution, our particular solution will be x raised to 4 minus 2x cubed t plus x squared t squared is equal to 9. And this is our answer. So we have this as our particular solution. Okay. So let's go back to Sir Michael. Sir Mike.
Hello. Okay. Sorry. So, okay. So, let me share my screen to you. Thank you, DJ. So, we will have another word problem. This time, it will be an RCL or RLC circuit. Okay, let me go. Okay, so this is the problem. An RCL circuit connected in series has R equals 180 ohms, C equals to 1 over 280 farad, L equals 20 henries, and applied voltage of, let me just move a little, of ET sine T, oops, just give me a second. Okay, so let me read it from my paper. ET equals to 10 sine T, assuming no initial charge on the capacitor, but an initial current of 1 ampere. At t equals 0, when the voltage is first applied, find the subsequent charge on the capacitor. Okay, so let's wait for my bit paper while still loading. Anyway, if you have any questions or comments, please write down in our comment section below of on our Facebook page, Twitter account, and Instagram account. It's taking a while. Okay, let's wait for this. Okay, for an RCL circuit or RLC circuit, we have already the form d squared q over dt squared plus r over l dq over dt plus 1 over lc times q and then equals to 1 over l et. So the q means it's the charge, and T, of course, is time. R would be the uh, ohms. Let me again unshare. Let me try sharing this again. Okay, it's bit paper is still loading. Okay, so hmm, give me 1 second for this to fix. Keeps on loading. Okay, let me use another virtual board. Sorry. Okay, so let me read again the problem. So we have an RCL circuit connected with a series of R equals 180 ohms. And then we have a capacitance of 1 over 280 farad. And then there's a L, which is our inductance of 20 henries. And then our voltage is E of t equals 10 sine of t. So with this kind of problem, we have to use this form of the solution. So d squared q over dt squared plus r over L dq over dt plus 1 over LC q equals 1 over L E T. All right. So what we need to do is let's substitute all of this given here to our equation. So I'm going to use the double dot form for our differential variable. So if it's q double dot means it's second differential or second derivative of that variable. So plus r is 180 over L, which is 20. And then this would be q. So 1 dot because it's just first derivative. And then 1 over L, so 20 times C, which is 1 over 280 Q. And then 1 over L is 1 over 20 times 10 sine of T. Okay, so mm, okay, so this is sine of T. And we can simplify this. So this is Q plus 9Q dot plus 14Q equal to 1 half sine of t, right? So if you notice, we can get the characteristic or the roots of the characteristic equation from the left-hand side of our equation. So let's go straight directly by using lambda. And then let's factor it out. So this means this is lambda squared plus 9 lambda. And then let's equate it to 0. So plus 14 lambda equals 0. Okay, let's go to another page. So this would mean lambda plus 7 equals lambda plus 2, right? Because it says lambda squared plus 9 lambda plus 14 equals 0, right? So lambda is negative 7 and lambda is equal to negative 2. So our general solution to the homogeneous equation would be Q of H is equal to C sub 1 e to the negative 2t plus C sub 2 e to the negative 7t. So we apply these two lambdas into the homogeneous equation form. And then on the right-hand part, which we see that it has the sine t or the sine function on the right-hand side of the equation. So this time we're going to use using the method of undetermined coefficients. So in this case, we have case number 3. So our form is phi of t is k1 sine of beta t plus k2 cosine of beta t. So the solution for this, if you have this form, would be y of p equals to a sine beta t plus b cosine of beta t. All right. So let's apply what we have. So in our case, we have k1 equals 1 half, beta 1 is beta equals 1, and our k2 equals 0. So in our case, we will adapt our solution based on the y particular solution given. So q of p in our case would be a sine of t. So since beta is 1, we don't write it here, plus b cosine of t. And then let's get the first derivative of qp. So q of p, so a cosine of t. And then the derivative of cosine would be negative sine. So b negative sine of t. And then gets the second derivative. So 2 dots of p. So again, this would become negative a sine of t. And then the derivative of sine would be cosine. So b cosine of t. Okay, so let's substitute in equation 1. So what is equation 1? So we said q dot plus 9q, oops, sorry. Q dot is 9q dot, only one dot, plus 14q is equal to 1 half sine of t. So our goal here is after we substitute these three equations here, we will actually be comparing coefficients of like terms. Okay, so let's try to substitute in our equation. So let's go to the next page. So I'm writing it out. Negative a sine of t minus b cosine of t plus 9a cosine of t minus b sine of t, and then plus 14a sine of t plus b cosine of t, and then equal to our voltage, or the right hand side will be 1 half sine of t. Okay, so let's go back to the left hand side. Let's collect all the sine function. So we have first is negative a. So this one here, negative a, and then what else? So negative 9b. So minus 9b. And then next is the here. So 14. So this would be plus 14a, right? And then quantity sine of t. Now let's collect all the cosine. So first would be negative b, which is this one here. And then next is 9a, right? So this one here is 9a. So plus 9a. And then the last would be the 14b. So plus, oops. So plus 14b cosine of t equal to 1 half sine of t. So equating coefficients, we will see that this part, this part here is equal to 1 half, right? Because the coefficient of sine t would be equal, right? So let's equate it. So negative a minus 9b plus 14a equals 1 half. So that's the other one. So since there's no cosine on the right hand side of the equation, so this part of cosine would be equal to 0. Negative b plus 9a plus 14b is equal to 0. Okay, let's try to simplify this. So this would be 13a minus 9b equals to 1 half. And then this one would be also be 13b plus 9a equals 0. So let's try to get a in terms of b on this one. So a would be equal to 13b over 9, right? And then let's substitute it here in this form, in this equation, I mean. So 13 times 13b over 9 minus 9b equals 1 half. So this would be equal to um so negative 169 over 9b minus 9b equals 1 half. So let's multiply everything by 18. So this would be negative 338b minus 162b equals 9. And this will give you b equals negative 9 over 500. So that's for our the b coefficient. And if we solve for a, so a is negative 13 over 9 times negative 9 over 500. So 9 cancels out. So this would be positive 13 over 500. So therefore we have our QP. So QP, we already solved QP is 13 over 500 sine of t minus 9 over 500 cosine of t. So this is our B and this is our A. So let's combine now the general for our general solution. QP and QH. So general solution is Q of t is Q sub H plus Q sub P. So Q sub H is C sub 1 e to the negative 2t plus C sub 2 e negative 70 plus 13 over 500 sine of t, and then negative 9 over 500 cosine of t. Okay? So now let's apply the initial condition. So given is Q of 0. So what's so no initial charge on the capacitor. So Q of 0 would be 0, but an initial current of 1 ampere. So there's an initial current. So if we take the derivative of charge, that's the current. So Q just 1 dot at 0 is equal to 1. So we need to get, so applying that condition. So if we take, so C sub 1 e to the negative 2 times 0 plus C sub 2 e to the negative 7 to 0 plus 13 over 500 sine of 0 minus 9 over 500 cosine of 0 is equal to 0, which is the initial charge. So what is left is C sub 1 plus C sub 2 minus 9 over 500, because this is 0. For sine 0 is 0, is equal to 0. So we have, let's define C sub 1 in terms of C sub 2. So C sub 1 is equal to 9 over 500 minus C sub 2. Okay, so let's say this is our equation. Let's take note of that. And then for the ampere or for the current, let's differentiate our Q of t. So Q dot, just one dot, is equal to negative 2 C sub 1 e to the negative 2t, and then negative 7 C sub 2 e to the negative 7t plus 13 over 500 cosine of t plus 9 over 500 sine of t. So it says there initial charge is 1 at time 0. So this means Q of 0 is equal to negative 2 C sub 1 minus 7 C sub 2 plus 13 over 500 is equal to 1. So let's rearrange this. So negative 2 C sub 1 C sub 2 equals to 1 minus 13 over 500. So this is 487 over 500. So let's substitute our value of C sub 1 from this equation. So we got C sub 1 is equal to 9 over 500 minus C2, right? From our earlier equation. So let's put it here. Okay, so negative 2. This will be 9 over 500 minus C sub 2 minus 7 C sub 2 equals 487 over 500. Okay, so if you manipulate this, so be doing the shortcut in the interest of time. So this would be C sub 2 is equal to negative 101 over 500. All right, so we got C sub 2. Now let's solve C sub 1. So C sub 1 is 9 over 500 minus minus. So this will become plus. So plus 101 over 500. So this means this is 110 over 500. Okay, so our solution would be, so let me write it, Q of t 110 over 500, which is our C sub 1, and then e to the negative 2t minus 101 over 500, which is our C sub 2, right? E to the negative 7t plus, of course, the particular solution 13 over 500 sine of t minus 9 over 500 cosine of t. So if you'll notice, as t, this is the sum oops. So the exponential part is actually are the transient part of our equation. So this is the transient. So if t goes to infinity, this would become 0. Look at the e. It has a negative exponent, so it will be in the denominator. So 1 over infinity would be 0. So both of this equation would be 0. And the second part with the uh, sine and cosine function, this is our steady state part. So even if t goes to infinity, it will not die out, right? Okay, so and the question there, oh, that's it. So we're not gonna solve anything after this. So this is our final solution. Okay, so let's go back to DJ. Let me share my screen. Okay, DJ, you can share your
Okay.
solution.
Okay. So let's proceed to our next problem. So we have here a differential equation that is dq over dt plus 2 over 10 plus 2t q, and that is equal to 4. Okay. Okay. So here, we can actually yes, we can actually cancel 2 in our second term. we have dq over dt plus 1 over 5 plus t q is equal to 4. Okay, that's for simpler solutions. Okay, so this equation, of course, by noticing our equation, this is not I think I don't think if it is variable separable. Yes, you can verify this on your on your own, okay, if it is variable separable or homogeneous. But this time I'll present to you another way of solving, because this differential equation is actually another type of a linear differential equation, which is the linear ordinary differential equation. So linear ODE, linear ordinary differential equation. Okay. So these types of equation is actually in this x and y. Okay. Since most of our equations are in x and y, but we can also use other variables. Okay. So we have dy over dx plus y times a function p of x must be equal to q of x. Okay, so this is a linear ordinary differential equation. And before we can solve for our general solution, factor. Okay, so the integrating factor is given by e, that is our multiplier to y in our differential equation. So after solving for the integrating factor, the general solution will be y times the integrating factor must be equal to the integral of q of x, that's the right hand side, q of x times the integrating factor, dx. Okay, then after that, you can solve for y, okay, to solve for the general solution. So for our problem, um, we have q and t as our variables, okay. So we can solve actually for right away for our integrating factor, that is e raised to the integral of 1 over 5 plus t. Okay, that is a multiplier for q from our differential equations. So this one, I'll just highlight it. And then, respect to t, okay, we'll disregard the arbitrary constant first. Okay, so integrating the exponent, we have the natural log of 5 plus t. Okay, so that is equal to e raised to the natural log of 5 plus t, we have 5 plus t. Okay, so that is actually our integrating factor already. So let's go directly to our general solution. So our general solution is q, that is y on our form, okay, that is similar to y, q times the uh, integrating factor, 5 plus t. That is equal to the integral of q of x, or that is the right hand side, that is 4, okay, times our integrating factor, that is 5 plus t dt. Okay, so using the power rule, the right hand side will be 2 times 5 plus t squared plus the arbitrary constant c. Okay, so this is actually our general solution, but since we are trying to solve for q, we can actually solve for q here. Okay, it's just by dividing 5 plus t. So solving for q, we have 2 times 5 plus t plus, we can use a negative exponent, so c times 5 plus t raised to negative 1. Okay, so and this will be our general solution for the linear ordinary differential equation. Okay, but if you can express the final answer or the general solution as a fraction, then so be it. as long as the value of q is the expression for q is solved. Okay, so let's proceed to our next problem. Another similar problem. We have 25 times d time dt capital T dt small t, okay, plus t, that's equal to 80 e raised to negative 0.04 t. Okay, we can have t here. I think usually for these kinds types of problems, we have t as the capital T sometimes is used for to denote temperature. Okay, and then t small t can sometimes be denoted for used to express or to represent time. Okay, just for but just for you to know. Okay, so our original differential equation is not yet in the form in this form. Okay, the linear or ODE. So, similar to this one. So how will we be able to rewrite the equation in this form? Okay, we'll just have to divide the whole equation by 25 so that the leftmost term will be dt over d differential of capital T over differential of small t. Okay, so dividing the whole equation by 25, we have d capital T over d small t plus 1 over 25 capital T is equal to 80 e raised to negative 0.04 t. Well, actually, this equation exponent of e, we can actually rewrite this as negative 1 over 25 t, so that we have um, we will deal with fractions only. Okay, so now I'm sorry, we just have to divide also 80 into 25. That is 16 over 5. Okay. So now we can solve for our integrating factor. That is e raised to the integral of the multiplier to t. That is 1 over 25 dt. Okay. So that is equal to e raised to the integral of the exponent. That's simply t over 25. So that will be our integrating factor. Okay, so solving for the general solution, we have t times the integrating factor of e raised to t over 25. That is equal to the integral of the right-hand side. We have 16 over 5 e raised to negative 1 over 25t times the integrating factor of e raised to t over 25 dt. Okay, so before we evaluate the integral, we can simplify actually the integrand. Okay, we can cancel the two exponential expressions since the exponents will cancel out, right? T over 25 minus 1 over 25 t is 0. And then e raised to 0 is 1. Okay, so we are left with t e raised to t over 25 equals the integral of 16 over 5 dt. Okay, so evaluating our integral, that is 16 over 5t plus our arbitrary constant. So solving for t, we'll deal with negative exponents. So we have 16 over 5 t plus c 25. Okay, as you may notice, the exponent of e is negative, so at just additional info, okay? So as t approaches infinity, t also approaches 0. Okay, t approaches 0. So that's it for this problem. I'll just highlight the general solution, our final answer here. Okay. Okay, so that's it for linear ordinary differential equation. Let's go back to Sir Michael.
Okay, so thanks, DJ. Okay, let me share again my screen. Okay, so this is another word problem. I put it here in my another virtual board because my other virtual board is not working. I don't know what happened. Okay, so a mass of 2 kilogram is suspended from a spring with a known spring constant of 10 newtons per meter and allowed to come to rest. It is then set in motion by giving it an initial velocity of 150 centimeters per second. Find an expression for the motion of the mass assuming no air resistance. So this is actually will be governed by Newton's second law. Okay, so Newton's second law will have this form. So x double dot plus a over m 1 dot plus k over m x equals f of t over m, which is force, m is mass, and a is acceleration. So what we know from our problem is that it's free undamped motion since there are no externally applied force from the outside, applied force on the mass. What else? No resistance, right? No resistance. Sorry, no resistance from the surrounding medium. Okay, and we have given. So what's our given? Given is, of course, our mass of 2 kilogram, and then our constant, right? The spring constant of 10 newtons per meter. What else? And then we have this velocity of 150 centimeter per second. All right, so let's substitute this in our Newton's second law equation. So substitute in equation 1. So this will become x double dot plus, of course, we don't have acceleration. Sorry, our f of t, yes, f of t is 0 and a is 0. F of t is 0 and a is 0 because of no resistance from the surrounding medium. So 0 of 1 dot x, and then 10 over 2 of x equals 0. So x double dot plus 5x equals 0. Okay, so this is our equation. So it's a second order linear differential equation. So what we can do is we can substitute x of t equals e lambda t. So it means double differential of e of lambda t plus 5e of lambda t is equal to 0. Okay, so let's take the derivative of x of t. So this one here, x prime of t, which is equal to lambda e to the lambda t, and the second differential of that, or double, whatever we can use, either prime or dot, this would be lambda squared e to the lambda t. Okay, so then let's substitute this to in our equation here. So this would give us lambda squared e to the lambda t plus 5e lambda t equals 0. Okay, and then we can factor out e lambda t. So lambda squared plus 5 equals 0. So let's equate this to 0, right? So we know that this part will not 0, right? Because our of any finite lambda. But this could probably equal to 0. So let's equate this to 0. So lambda squared plus 5 equals 0. We can see that lambda is a imaginary number. So negative 5. So let's put the square root. And then lambda is square root of negative 5 plus or minus, of course. So let's take the form of I. So lambda plus or minus square root of 5, take out the I, or square root of negative 1. So we know that I is equal to square root of negative 1. So this would be our two roots. So x1 of t, oops, x1 of t would be equal to c sub 1 e to the I square root of 5t, and the other one is x sub 2 of t be equal to c sub 2 e to the negative I square root of 5t. So our general solution will be combining these two x. So x of t is equal to x sub 1 of t plus x sub 2 of t, which is c sub 1 e to the I square root of 5t plus c sub 2 e to the negative I square root of 5t. Okay? So we have 8 minutes more, and then um, if you remember your Euler's identity, so I think we will have an extra uh, additional time of 5 minutes. So E is lambda plus I beta, right? This is equal to E to the alpha, not lambda, alpha but cosine of beta plus I e to the lambda sine of beta. So if we will apply this into our case, so our alpha is 0 and our beta is actually equal to square root of 5t. So x of t would now be equal to c sub 1 e sub 0 cosine of square root of 5t plus I e sub 0 sine of square root of 5t plus c sub 2 quantity e sub 0 cosine of square root of 5t, and then plus minus e sub 0, of course the I sine of square root of 5t. All right, so when we rearrange this, this is our final equation. Okay, let me show you, because there are actually arbitrary constant. Oops. So x sub t is c sub 1 cosine of square root of 5t plus c sub 1 I sine of square root of 5t, and then plus c sub 2 cosine of square root of 5t minus c sub 2I sine of square root of 5t. Alright, so when we rearrange this, it will be c sub 1 plus c sub 2 cosine of square root of 5t plus I c sub 1 minus c sub 2 sine of square root of 5t. Okay, so we can redefine c sub 1 plus c sub 2 as our c sub 1, and then our I of c sub 1 minus c sub 2 would be our c sub 2. Okay, so our final equation would be x of t c sub is equal to c sub 1 cosine of square root of 5t plus c sub 2 sine square root of 5t. Okay, actually there is an initial condition. It says there at t0, equilibrium position is x sub 0 equals 0 meter. So x sub 0, let's apply it into our solution. C sub 1 cosine of square root of 5, and this is times 0 plus C sub 2 sine square root of 5 times 0, which is t, and equal to 0. So C sub 1 to 0 equals 0. C sub 1 is 0. Now so what is left is C sub 2. So C sub 2 sine of square root of 5t. Okay? So now let's do our initial velocity. Okay, just 2 minutes more. V sub 0 equals 150 over centimeters per second. So that is 1.5 meters per second, right? If we change centimeter to meter, and then let's differentiate x of t to get our velocity. So v of t, right, would be x dot of t. So that's the differential of x of t, which is equal to velocity. So let's differentiate this. So this would become square root of 5 c sub 2 cosine of square root of 5t, right? Okay, so it says at v0, the velocity is 1.5 meters per second. So cosine of 0 equals 1.5. So c sub 2 is 1.5 over square root of 5. So our final solution would be x sub t 1.5 over square root of 5 sine of square root of 5t. So this is our final solution. So let's go back to DJ for the two final differential equations. DJ, it's your turn. Okay, if you have any questions or comments, please write it down on our comment section below, in our Facebook
Okay.
account and our Twitter
So we
account and
have
Instagram
our
account.
last two differential equations. Actually, the second to the last problem is actually somehow, yes sir, yes sir. Can you hear me?
So let's wait for DJ to get connected again. He will still solve two more equations. Okay, he's online now. All right.
Um, okay, sorry for that again. Okay. Okay, so we are down to the second to our second to the last problem. Okay, so the our second to the last problem is not actually a differential equation, but this computation is used in differential equations, and it's actually used in the method of variation of parameters, which is called the Wronskian. So we are asked to evaluate the Wronskian of x cubed and the absolute value of x cubed in the interval -1 to 1. Okay? So as we notice, the absolute value of x cubed, okay, is equal to x cubed, positive x cubed, if x is greater or equal to 0, but it is negative x cubed if x is less than 0. Since the two intervals, okay, are present in our given domain, restricted domain, then we will evaluate the Wronskian involving our absolute value. So to determine our Wronskian, we must take we must determine the determinant. We must calculate the determinant of a matrix. Okay, since we have two elements here, so we will have a 2 by 2 matrix. we write the first row as the elements. Okay. Okay, I'll just relocate some variables here. Okay. So the first row will be our given elements, and then the second row will be their derivatives. So the derivative of x cubed is 3x squared, and then the derivative of the absolute value of x cubed is actually 3x squared times, okay, the absolute value of x over x. Okay. Okay. So by taking its determinant, this will be actually cross multiplication and subtraction. Okay, since it's a 2 by 2 matrix. So the determinant of this matrix will be x cubed times 3x squared absolute value of x over x minus, we have 3x squared, okay, 3x squared times the absolute value of x cubed. Okay, so we'll try to simplify the first term. This is actually 3x to the fourth, the absolute value of x. And then we have 3x squared. The absolute value of x cubed, okay, can be written as x squared times the absolute value of x. Since x squared, okay, I'll just write it here. See, because x squared is greater or equal to 0 at any value of x. Okay, so we have this expression. Now, let us simplify things further. So we have 3x to the fourth absolute value of x minus 3x to the fourth absolute value of x. Of course, it's obviously uh, evident that our answer is 0. Okay, so the Wronskian here is 0. Right. So let's proceed to our final differential equation. We have a second degree linear homogeneous differential equation. We have y double prime plus 4y prime plus 5y is equal to 0. Okay, so let us consider other notations so that we can solve this easily. Let's have y double prime. Since y double prime is the second derivative, we'll try to rewrite it as a differential operator in the differential operator form. Okay, so we have d squared y plus 4 dy since the first derivative of y, and then 5y is equal to 0. So we can try to factor out y. So we have d squared plus 4d plus 5 times y is equal to 0. From there, we can actually derive or solve for our characteristic equation. The characteristic equation is this one, the multiplier to y. So we have d squared plus 4d plus 5 must be equal to 0. Okay? So solving for d, you can use any method that you know, but I'll just have its solution here. Negative 2 plus or minus the imaginary number I. So if we have the roots of a characteristic equation as a complex number, that is when it's in the form, I'm sorry, it's in the form a plus or minus b times I, then our general solution will be e raised to ax, or any independent variable as e raised to ax. Then we have c1 cosine of bx plus c2 sine of bx. Okay, these are derived a while ago by Sir Michael. Okay, so this is actually our general solution for for that given root of the characteristic equation. So from our solution here, our general solution will be e raised to negative 2x times the quantity c1. Okay, b, the value of b here is 1, so we have c1 cosine of x only, and then plus C2 sine of x. Okay, so from there we already have our general solution. Okay? It's actually that fast to solve for this. It's actually quick to solve. Okay, homogeneous higher order linear differential equations. Once that the right hand side is not equal to zero, then we will have to solve two times. Okay, and that's it for our discussion. Okay. Sir.
All right. Thank you, DJ. Before we end, I'll just want to show the problem I did for problem number 3 so people would see how it is written. So let me, for the last time, I will share my screen because they only see how I solved it. But this is the actual problem. So if you're taking picture of this one, I'm just showing this to you guys. So that's it. Okay, so there you go. Okay, thank you very much for watching us tonight. Thank you, DJ, for joining me as well. And we will see you again next Thursday. And to all our followers who send their questions from Monday to Wednesday, that's PST, Tuesday to Thursday, Manila time. We will be solving them via Facebook Live on Thursday, Friday, Manila time. Okay, see you next Thursday. God bless. Stay safe and be happy. Thank you.